Experiment 5 has the goal of giving you practice in skills related to heat transfer and calorimetry experiments. And the experiment will be done in the context of obtaining data for use in a Hess's law calculation. We'll be using glassware in this experiment, so standard glass safety rules apply. Make sure you check for cracks and chips and discard any broken glassware. We'll also be making a solution that gets fairly hot, so you should be careful to avoid touching that solution. In this experiment, our hot solution will be held inside insulated coffee cups, and those will be held inside a beaker, so you should be fairly safe from burns. We'll also be using magnesium metal, which is flammable and burns with an extremely intense light, but the fire risk in this lab is very minimal because magnesium doesn't ignite until it gets extremely hot, and we won't be using any open flames. We will also be using magnesium oxide, which is a basic chemical and is therefore corrosive. It's also a fine powder, so it's an irritant. And the dangers associated with both of those hazards, corrosive and physical irritants, are that you can damage the skin, the eyes, and the lungs. So to minimize these risks, you should avoid getting the magnesium oxide onto your skin, into your eyes, or breathing it in. And if you do happen to get any on you, you should wash the affected area with water. The final chemical that we'll be using in the experiment is 1 molar hydrochloric acid. The 1 molar indicates that it's a fairly dilute solution and that many of the hazards are going to be minimized. The primary concern with dilute HCl is that it is corrosive. And like with any corrosive material, you should avoid getting it on your skin, in your eyes, or breathing it in. If you do manage to get in contact with the HCl, remember that it's fairly dilute and you can wash it off with copious amounts of water. The procedure for this experiment is broken into 2 parts, but since the procedural steps for both parts are almost exactly the same, we'll only be talking about the first part in this video. To start, you're going to make a simple coffee cup calorimeter by stacking 2 styrofoam cups inside one another to provide insulation, placing them inside a 250 milliliter beaker for stabilization, and then covering them with a plastic lid. And make sure that the temperature probe for the LabQuest fits nicely inside the lid. Then you should measure out exactly approximately 50 milliliters of dilute hydrochloric acid into a graduated cylinder and then transfer that HCl into your calorimeter. You should record the volume measured in the graduated cylinder, and you should record the exact molarity of the acid as well. You should then put the cover back on top of the calorimeter, insert the temperature probe, wait for the temperature reading to stabilize, and then record the initial temperature of the solution. You should then weigh exactly approximately 0.5 grams of magnesium directly onto a watch glass, and you should then record that mass. Then you should add all of your magnesium to the calorimeter, put the cover back on, and then begin recording the temperature every 10 seconds while simultaneously gently swirling the calorimeter. The temperature should rise steadily and then plateau at a maximum temperature and then start to drop back down towards room temperature. And then stop recording roughly 2 minutes after you think you've seen the maximum temperature. You should end up with a data set that looks something like this, where you have time intervals of 10 seconds and temperature readings corresponding to each of those time intervals. Somewhere towards the end of your data set, you should see that the temperature stops changing very rapidly, reaches a maximum, and then starts to fall. In order to find the true maximum, you'll need to plot your data, and you should do that with temperature on the y-axis and time on the x-axis. Plot each of your data points, and then extrapolate to find the true maximum by drawing a straight line that passes through the maximum temperature that you observed and all of the data points that come afterwards. And the point where that line intersects the y-axis is the true maximum temperature. And you should then record that value in your data table. Once you've done this, you can then dispose of your calorimeter contents, which may be very slightly acidic, by pouring them into an acid and base waste container to be neutralized later. This container is going to be in a clearly labeled fume hood. You can then rinse your calorimeter and probe clean with some distilled water and dry them with paper towel and reset before doing the next part of the procedure, which involves magnesium oxide. The calculations that you'll need to do are all based on this heat transfer expression, Q equals mCs delta T. The delta T is just the difference between the maximum temperature and the initial temperature. The m is the mass of all the material that's involved in the heat transfer, and in this case we're going to make the assumption that since we're working with a dilute solution, we can simply use the mass of water involved. And to get that, you can use the volume of acid, and we're assuming that because it's dilute, the density of that solution is equal to the density of water. The Cs is the specific heat of the material involved in the heat transfer. And again, because we're working with dilute solutions, we'll use the specific heat of water. And Q is the amount of heat that's transferred, and we can use that to find our enthalpy. And it's important to remember that Q at constant pressure is equal to the change in enthalpy. And the calculation section of the report asks you to find the enthalpy of reaction between magnesium and HCl in units of kilojoules per mole of magnesium. So that means kilojoules per mole of magnesium that actually reacted. So you'll need to do a limiting reagent calculation for the reaction of magnesium and HCl to find out how much magnesium actually reacted. You can use the mass of magnesium to find the moles, and you can use the volume and molarity of HCl to find the number of moles of HCl. And if you balance the equation between magnesium and HCl, you can get the stoichiometric coefficients that you need to do that limiting reagent calculation. All you have to do then is convert your heat transferred into units of kilojoules and divide by the number of moles of magnesium that reacted to get the enthalpy change in kilojoules per mole of magnesium. And at the end, make sure that you put the appropriate sign on that value. And the calculations for part 2 of the experiment for the reaction of magnesium oxide and HCl will be done in a very similar fashion.